Okay, so in quantum field theory, as we will see shortly, the delta function, well, more generally, position r, say, minus r naught, this kind of object is essential in finding solutions to the equations for interacting fields. And so notice that this object has infinity at its heart. And so this is also a place where one can reflect and do some philosophy. But infinity is essential here. And of course, quantum field theory is one of our fundamental theories. And so infinity is essential. It's really at the foundations of physics. So we want to review this delta function. Let's start by doing this in one dimension. So if we say x minus x naught, then this quantity is defined such that this is 0 if the value of x is not equal to x naught. X naught is some positive number, say. It could be a negative number. It's any x value, but it's a specific value of x. But if x is equal to x naught, right, then we get infinity. And we do it such that infinity times 0 in this object is equal to 1. So here is, if we think of integrating this function from over all of x, then we get no contribution for all values of x that are not x naught, and when x is equal to x naught, we get infinity. But this is a specific case where infinity times an infinitesimal is equal to 1. So we can really think of this as, here's our function delta x minus x naught, and this is x, and here is x naught. Then we can sort of build this function by making a narrow or a narrow spike. This is sort of the limit of some other function, but I can't really draw the function itself, so I'm going to draw it as we're sort of approaching that limit. It drops quickly to 0 and then spikes at the value x naught. Right, quickly drops to 0, more and more quickly drops to 0, and then in the limit this goes to 0 here and goes to infinity there, but such that, right, this is kind of like the area here, right? The area there, and that area is equal to 1. Okay, and so for functions, for continuous functions, let's say g of x, then if we do g of x times the delta function, this is 0 everywhere except at x naught, so this could be interesting only at the value x naught, and therefore it tells us, it suggests that we should be thinking of x naught here, and so this is just g of x naught times x minus x naught. That's the only place it could be interesting, and if we put it under the integral sign and we do this operation, then we just replace this, right? That's just that constant, whatever that constant is, and then we have, of course, what we're familiar with at this point, and therefore this is just equal to that constant, the value of that function at that location. And so maybe we can look at this in 3D. In 3D, this looks like we're integrating over the entire volume. And so we have a function that looks maybe like that, r minus r naught over volume. And if we think of x, y, and z, right, so coordinates, then we're doing x, y, and z, separate integrals. Then we can break this up into an x minus x naught right? The r naught has x naught, y naught, z naught values, and so the function looks like this. And dx, dy, dz, and this thing is equal to 1 as per that. So that's sort of a reminder of what we've done before. You've seen that before, either in electromagnetism or in quantum. Let's specifically show that the delta function appears in this kind of a quantity. So we take the divergence of a vector, and that vector is the unit vector, r hat over r squared. And so we're doing the divergence. Well, let's write this out in some coordinates. So we could do it in different coordinates, but maybe it's easier. Well, I'm not sure it's easier, but let's just do it in Cartesian coordinates. So the divergence is d by dx I hat plus d by dy j hat plus d by dz k hat, and that's being applied to this vector. So r hat is just, right, r is x I hat plus y j hat plus z k hat, that's r, and we want to divide by r squared. We know that r squared is x squared plus y squared plus z squared, but we want an r hat here, so we really have an r over an r cubed. So we need an r cubed here, and so this becomes x squared plus y squared plus z squared, not to the 1, but to the 3 halves, because we have x squared plus y squared plus z squared times r, and r is just x squared plus y squared plus z squared to the 1 half. So here we have a 3 halves. It looks like that. So let's break this up. So this applies to the part with the I hat, and so we have d by dx of x, so we don't need the I hat. Well, it goes away because we have I hat dot I hat. That just becomes 1. So we have x, we have d by dx applied to this, so it's x over x squared plus y squared plus z squared to the 3 halves plus d by dy applied to, we see that there's symmetry here. So we have a y over x squared plus y squared plus z squared to the 3 halves plus d by dz applied to z over the same common factor here. Looks like that. So we really need to do this operation only once because we know what it will look like by symmetry. So here we have, okay, so really we have an x times an x, so x times this thing to the minus 3 halves. So we first, by the chain rule, we would do dx by dx, that's just 1. So we have 1 over x squared plus y squared plus z squared to the 3 halves, because it's just this term. And then we apply it to the other term, to this thing. So we have an x there, but we have a minus 3 halves. Here's the x. And then we have the x squared plus y squared plus z squared. That's to the minus 3 halves. So we do minus 1s, we get minus 5 halves. And then we apply it to, we're doing a d by dx, so we get a 2x from that. And then, of course, by symmetry, we have something similar for all of these other, for these two. But in terms of y, as opposed to x and here, and z here, as opposed to x and y for the first two. So let's see, what does that give us? So we get 1 over x squared plus y squared plus z squared to the 3 halves. And then we have a minus 3 x squared over, 2's go away, x squared plus y squared plus z squared to the 5 halves here, plus dot, dot, dot. So we have terms like this with y squared and z squared. And so overall, we end up with we also have 3 of these here. So we have 3 over x squared plus y squared plus z squared to the 3 halves minus 3 times x squared plus y squared plus z squared over x squared plus y squared plus z squared to the 5 halves. And so that becomes, let's pull the 3 out, that becomes 3 times 1 over plus z squared to the 3 halves minus, we pull the 3 out, we have 1 over x squared plus y squared plus z squared to the 3 halves. Right, when we simplify there, and so notice that this is, well, so it's infinity if x equals y equals z equals 0, right? We're dividing by 0, so we get infinity, and it's equal to 0 otherwise, right? Because these are finite numbers, and they must be equal to each other, and we're subtracting them, so we get 0. So in fact, this object is the delta function. So we can say that divergence of r hat over r squared is equal to delta r. And so we'll be using this kind of thing later on to find the solutions of interacting fields in quantum field theory.